Vibe coding has transformed software development. People who couldn't write a line of Python are now building apps. But there's one domain that hasn't had its vibe coding moment yet: hardware design. I want to introduce you to vibe architecting. Now, why did I build this? The demand for silicon is at an all-time high. Every AI chip, every data center GPU, every smartphone processor starts the same way. An engineer sits down and manually writes Verilog, a hardware description language that translates architecture ideas into actual circuit designs. The problem is that this process is brutally slow and expensive. Industry data shows that verification alone consumes 70% of total chip development effort. Only 14% of designs succeed on the first silicon tape-out. And a single mask set costs tens of millions of dollars. Every mistake, every respin is a gut punch to the balance sheet. The RTL design skill set is concentrated among a very small and niche group of engineers, primarily at companies like Intel, NVIDIA, and Apple. I'm about to go deep into this field myself, and even before I did, I noticed something obvious. Why hasn't this been automated the way software has? Vibe coding exists for Python, for JavaScript, for web apps, but nobody had brought that same energy to Verilog. So I built Spec2RTL, a fine-tuned model and agentic pipeline that takes natural language architecture specification and generates working, verified Verilog RTL. I'm calling this vibe architecting. So how does it work? The system has 3 layers, each built on top of the last. Layer 1 is the fine-tuning. I started with a Qwen 2.5 coder, which is a 32 billion parameter model, specifically built for coding. And I fine-tuned it specifically on Verilog using QLoRa, a parameter-efficient training technique that let me train a 32 billion parameter model on a single H100 GPU. The training data combined open source Verilog repositories with synthetically generated instruction pairs that I created using Claude Sonnet, which spent a lot of my money, $100 worth. I evaluated everything on CVDP CID003, which is a benchmark of 78 Spec2RTL problems created by NVIDIA engineers specifically to test whether AI can do the things that their own teams do every day. This alone got me from 14% benchmark pass rate to 19% with the fine-tuning, but I knew we needed to make more progress. So, layer 2, which was reinforcement learning. Fine-tuning techniques teaches the model to imitate good Verilog, but I wanted to actually learn what correct hardware behavior looks like. I applied GRPO, a reinforcement learning algorithm, using a tired reward signal. Full credit if the RTL compiles and passes functional simulation, partial credit for compile only, and 0 for failure. This pushed the pass rate from 19% to 29%. Then came layer 3, the agentic loop. This is where things got interesting. Even the RL trained model fails on complex problems, so I built an agentic pipeline where Claude Sonnet acts as a reflector. It reads the generated Verilog from the generator, reads the error from the simulator, diagnoses the root cause, and writes a targeted fix instruction back to the model. The loop runs up to 7 iterations. I added 3 key improvements in version 11. A spec clarification step where Sonnet rewrites the spec as explicit implementation requirements before generation. Error categorization, so the repair prompt is specialized for timing bugs versus FSM bugs versus arithmetic bugs, and architectural reset trigger if the model keeps making the same mistake. The final result is that I was able to get 59% pass rate on the CVDP CID003 benchmark, beating Claude Sonnet standalone at 55%. A specialized fine-tuned open source model beating a frontier closed source model at this specific task. Now, what are the use cases and impact? The immediate user is the RTL engineer at a company like NVIDIA or Intel. Right now, they spend enormous amounts of time writing boilerplate Verilog for components they have mentally already designed. Spec2RTL lets them describe what they want in plain English and get a working starting point instantly. They can refine it rather than write it straight from scratch. But the long-term vision is bigger than this. As the technology matures, it democratizes hardware design the same way vibe coding democratized software. A chip architect who thinks in systems and algorithms shouldn't need to be a Verilog syntax expert. A hardware startup shouldn't need a team of 10 RTL engineers to tape out their first chip. The UI I built demonstrates this. You type a hardware spec in plain English, the model generates Verilog and renders a block diagram of the circuit in real time. You can toggle between Claude Sonnet and my fine-tuned Quen model to see the difference. Anyone can clone the repo, add their API key, pull my adapter from HuggingFace, and start vibe architecting. Now, what would I add if I had more time and compute? Well, a few directions I'd pursue. First, closing the agentic loop for general use. Right now, the repair iterations rely on the test benchmark, or the test harness specifically, which requires pre-written test vectors. This kind of simulates how it would work in a real setting, where you would be writing tests as an RTL testing engineer. But a truly general product would generate its own test benches and run its own verification fully autonomously. Second is scaling the RL training. I was constrained to 60 GPU hours on a single H100. With more compute, I'd run more GRPO iterations with a richer reward signal, including formal verification results and not just simulation. Third, I'd love to extend this beyond Verilog to other HDLs like VHDL and System Verilog, and integrate directly into existing EDA tool flows so engineers don't need to leave their existing environment. The foundation is there. The benchmark results prove the approach works. Vibe architecting is real. It just needs to be scaled. The code, the model weights, and the full training pipeline are all open sourced. You can find everything on my GitHub, and the model adapter is on HuggingFace. Thank you so much.